So we're going to go over recommendation systems. It's going to be mostly a review of what we did. So I've added a few extra slides. I've removed some slides. I'm focusing on the core ideas. Please, if you do not follow, interrupt me, ask questions, make sure you understand it. The lectures which follow after this are going to get a little bit more involved, so it's important that you at least understand this material fairly well, okay? Especially focus on towards the second half of the lecture. The first half is mostly to remind you about how we go about designing recommendation systems, but when we get to doing the UV decomposition and stochastic gradient descent, so please focus and make sure you understand what the steps are. So we're going to do this. We talked about defining the utility matrix, which sort of tries to characterize how much a particular user likes a particular item. You can think of it as a matrix where the users are represented on the rows and the items are on the columns. And depending on how we look at it is which users like or rate, how they rate different items, or which items are rated by by which user. So you need to think of this, that the data can be coming in from very different sources. You could have a Boolean source, which is like, have you watched a movie or not? Have you visited a web page? It could be an ordered set, maybe a rating from 1 to 5 or 1 to 10, where the user has explicitly specified how much or how likely they are to like something. It could also be a real value if it's coming from a more complicated analysis. Some of the machine learning cases are going to generate values. If you're looking at comparison or similarity between, say, two images, you might have a real metric for measuring that. Keep in mind that the matrix is sparse. I mentioned this earlier, that in almost all the large-scale problems that we consider, you're going to end up with matrices just sparse. There's very little information internally, although the problem itself looks much larger. So we have millions, maybe billions of users. We have, again, millions, billions of items, but the level at which you have ratings available, or if you consider, say, the Netflix example, the number of movies that a particular user might have watched is going to be small. It's not usually going to be the same range as every user having watched or bought every single movie or product. The goal, the central issue that we're trying to do is that these are sparse matrices. If you consider the issue of assigning ratings to movies, then what we would like to say is that you have watched a bunch of movies and you have possibly rated them. We would like to get an estimate for how you would rate all the other movies that you haven't watched. When we start off from the data side, we don't have any information about these entries. These entries are blank entries in the utility matrices, in the matrix, where we don't know whether you like something or not. From a perspective of a recommendation system, it's also important to say that, again, I mentioned that the actual matrix is too large. So it doesn't make sense for us to predict all the blank entries. What we are potentially interested in from a recommendation perspective is that we like to predict some of the high entries. We don't even need to predict all the high entries. We just like to have a probability estimate of which particular entries, which items, which movies, which products you are likely to favor. We talked about two major approaches, and depending on the kind of system that we are designing, one of them might be preferable. You have content-based systems which try to characterize all the items they have by some features or some properties. We like to define users using the same set of properties, although the implications are a little bit different. Those properties, when assigned to a user, are an indication of where the user's preferences lie as far as those properties are concerned. A simple example could be maybe classifying movies based only on, say, the genre, or maybe a combination of genre, which actors are in the movie, who the director is. And so you can think of characterizing a movie now based on these factors. At the same time, you can characterize the user based on which of these properties they like. And the general idea is that you want to find items, movies, products, similar to the ones that the user likes. So this is primarily driven by item similarity. Of course, we can define user similarity here again because we have sort of taken the common ground of defining these properties which connect items to users. The second idea is to use collaborative filtering, and this is where we focused more, which tries to define a relationship between users and items. And we define this in terms of not having explicit properties for the items or the users, but saying instead that two items are similar if the same kind of users have expressed interest or bought those two objects. At the same time, two users are similar if they have purchased the same kind of items. So you can use, so to say, the rows and the columns of the utility matrix to define a way to compare users or items. Okay? And this is what I just talked about. In both approaches, whether we define properties for an item or a user, or if we use rows and columns of the utility matrix, we do need to define some metric which compares how similar these vectors are. And two very common choices for this are to use the cosine distance, which is basically a projection scheme, and the Jacquard distance, which tries to estimate what is the ratio between the intersection of the two sets and divided by the union. So it's how much of an overlap there is between two given sets. So yeah, the general idea is the recommendations themselves are based on finding similar users and then recommending items liked by similar users. So you try to find other users who have purchased items similar to you or have watched the same kind of movies, and then try to recommend the other movies which you might not have watched or products that you might not have purchased. The important difference here is that there are two approaches that we can use to estimate the missing entries of the utility matrix. So if we go for the collaborative filtering approach, we have some missing entries that we need to fill in. And so we can find similar users and average their ratings for a particular item where we might be missing an entry. Or we can find similar items and average the users' ratings for those items. The first approach is generally preferable because it's going to be more scalable, because you only need to find a similar set of users once, as opposed to finding similar items for every single item. It just generally scales better in terms of the number of times that you have to do it. The second approach, of course, is much more reliable. We talked about this as well, that you might, if you consider music as an example, two users might have a shared taste in rock music, but one of them might like bluegrass and the other one likes classical. And that does not necessarily hold, because users are much more complex, whereas items themselves are more likely to be one-dimensional. So it's much more reliable if you try to group items together. But there is a scalability issue here. Based on this, we can go for a clustering-based approach, which is that we have missing entries, and so we don't want to do this. We can iterate between them. And what we start off by doing is that we start clustering between items and users. So we have millions and billions of items. Similar to the previous lectures where we considered clustering, you can use your favorite clustering method to cluster items now together based on their similarity. Whether you opt for a collaborative filtering approach or a content-based approach, the similarity now is going to be defined based on whatever your similarity is, which could be the properties or the set of users who have purchased the same item. So you can cluster these together And here in this case, even if you use a k-means approach, we are not going to be clustering in a very aggressive fashion. We are only going to be clustering in a very low sense. So you would probably go for, if you had n items, you probably try to cluster it into n over 2 or n over 3 to basically reduce the size of it and to be able to map on. After we have clustered the items, we can create a new utility matrix which has entries which are the average from what the ratings that the user gives to those particular items in the same cluster. So you can average it out. So if you're missing some entries, it's fine. These are the non-zero entries that you map out. Once that is done, you can go ahead and cluster the users. So first cluster the items, then cluster the users, and then you can recurse until the matrix is sufficiently dense. And once you have a dense matrix, that's what you started off with. So this is a scalable approach for filling out the entries. Remember, we talked about that the original matrix, the size of the matrix is very, very large, and it's not really practical for us to estimate a dense matrix for that. But in this clustered form, you have a smaller matrix, both in the number of items and the number of users, so it makes sense to get a dense estimate out here. Once we have a dense utility matrix in this clustered sense, we can go back and recover the entries on a demand basis. We're not really estimating the full dense matrix. So given that we want to figure out to which cluster and an item, so you're given a user and you want to predict whether what sort of a rating this particular user is going to give item I, you figure out which clusters they belong to. If that entry for that particular cluster of user and item exists and it's non-zero, then you can just return that value for user I and item I. If not, you will use the same idea as earlier to find similar users or similar items. This is a much smaller matrix, so those approaches are now doable. Is this clear, the clustering approach? This is similar to what we're doing. So fundamental idea is too large a problem, we want to generate a coarser representation. Okay? The same idea will be used elsewhere. Why is it that this works? Or in which cases will such an approach not work?
So when you're finding the CD entry in the line,
yes.
Why don't we just use the dense manner?
It is the dense. So there are two cases, and this is just expanded out. If entries C and D exist, that's it. That's your value.
If C and D exists in the original matrix, you want
sorry, not C and D exist. If the
C and D are the dense.
No, C and D are the clusters.
Yes, clusters.
To which the user and the item belong.
Yes.
So in this dense, the smaller dense utility matrix that you generated after clustering, if an entry corresponding to C and D exists, then you're done. That's the same entry that you decide to use for you and I in the original matrix. If it doesn't, then we have to again go back to our original case, how we were doing it or how we proposed to do it.
But when you say the dense matrix has, you would try to populate the value for the dense matrix, or would you go back and
you would populate the value for the dense matrix by finding similar users or entries.
And then use them again and again.
So there is a trade-off here, right? So the trade-off here is, and you need to understand and appreciate this thing. Theoretically, I can keep clustering till maybe I have a single entry, which is filled, right? Which is the average rating that all users have given for all items, right? You can do that. But you don't want to do that because then the amount of information that is retained, you're losing information as you cluster, right? You might have rated two separate albums, say by the Beatles, as 4 and 4.5. When I cluster them together based on items, they're going to get averaged out, which means that you're losing information. Instead of being able to distinguish between saying that you like this 4 and 4.5, you're only getting something which is an average value of 4.25. Which is good in cases where you don't have any information, but in cases where you do have information, you're losing it. So your goal when you're clustering should be to cluster the right amount. That's why you're not clustering very aggressively. You're doing it in a hierarchical fashion so that you can stop at a stage where you can. Since we have this whole hierarchy, you can potentially even go back. You can set this up like almost like a pyramid and say that I want to go back and choose the most accurate value I have and not just use C and D.
Just before it became non-blank.
Yes, you could do that. We are avoiding complications here. But fundamentally, there is a trade-off. You don't want to cluster too much. So your parameters are going to be chosen so that your matrix is somewhat dense, but not to the extent where all entries are non-blank, right? And so you are going to end up with the second situation. So you can come up with simple heuristics here, and unfortunately, heuristics are what are going to work here because you can't, unless you analyze every problem independently, every specific recommendation system, and in a way that as new data comes in, more users are added or more items, you might have to go back and revisit. Using simple heuristics like saying that if my utility matrix, the quotient version, is, let's say, at least 25% dense, maybe I stop, or maybe 50% dense, depending on the kind of information and the quality of the ratings that you have. You're going to have to stop at some point. Fundamentally, this is related to what we'll cover in depth in the next lecture, and what we're going to go for next is that we really need to have an estimate of the rank of the matrix, which is sort of a measure of how much information is there, how much unique information is there. The idea of clustering here, whether we cluster based on items or cluster based on users, is saying that there aren't in reality a billion types of users. There are maybe 1,000 types of users. Keep in mind, I'm not distinguishing. You need to distinguish between what you would call as a type of user and a user, right? So if you are focusing on music, saying that yes, there are maybe 20 genres out there, and you're looking at that any given user would have a choice in 2, 3, 5. So we can classify the total number of variety of users who exist, right? And that is still going to be less than every single combination possible, right? It's not really going to be some sort of a number of genres factorial choices. It's a much smaller set of tastes that people would have. The same is true for items. It's not that I'm going to have a different rating for every single kind. You as a user might say that, I like these kind of movies, which means that there is, and this is the reason why your recommendation systems work in the first place, because you can say with high probability that the user is going to like another item. And that's what we are going to do to cluster these together, saying that I don't need to distinguish every single movie or every single album or every single product out there. I can start grouping them together. Knowing exactly how much to group or when to stop grouping is a difficult problem. And the way we can do it is to look at data, and we'll focus on this more deeply in the next lecture. In your high school, probably, you would have done sort of linear equations. It's not exactly a linear equation, but think in terms of the number of values in U and the number of values in V. So it's going to be ND plus DM, right? Those are the number of unknowns that we have, right? Based on these, wherever M is blank, we are saying that Mij is some product of a row in U and a column in V, right? A dot product between those two. Then what I'm saying is that that is an equation, isn't it? So it's an equation with ND plus DM unknowns. So in an ideal scenario, assuming it's going to be a very complicated system, but assuming we can set up a linear system of equations and solve it, right? But setting up this actual set of equations is a harder problem than what we are trying to solve. It's a larger problem. So that's not going to work directly. So we're going to use other approaches. Before I go into gradient descent, think of how we have this. We have a function out here. This norm that I have defined, M minus UV, defines a function which is a measure of how close my approximation UV, made up of these ND plus DM unknowns, matches M, correct? So what do we have here? We have a function of this many variables, correct? So that value is going to change. So I have basically, let's see, some f of, so gradient descent. What it means is that given a multivariate function fx, it's similar to the function that we just talked about. At some point, this is just, let's say, your guess for what the value of x is, right? Then we know that the value at a point b, which is basically in the negative direction of the gradient of the function f, is less than the value at a. Another way of thinking of this is if you're standing on a hill, you're going to go lower if you slide down the slope. If you go along the slope, then you're going to go to a higher position, right? So this is hill climbing or gradient descent. Gradient descent if you want to get to the maximum, right? Of course, the first order optimality also tells you that given a function, the derivative is 0 or the slope is 0 at a minima or at a maximum, correct? So you can use these two characteristics to decide how to walk along. So the general idea of gradient descent is that you start off with some guess, right? We start off with some guess for u and v. And then now we'd like to move about our space and get to a position which is the minimum, okay? So think of a lot of valleys and hills, and you're randomly thrown somewhere, and your goal is to get to the lowest point, right? What are you going to do? You're going to look around, you're going to say, it's changing most rapidly out here, which is the gradient. I'm going to walk in that direction. And that's the general idea that you do. Of course, how much you're going to walk about before you survey again is a tricky question. That's why there is a small factor. So maybe in our case, you take a step and then you again look and say, okay, I need to go this way. Then I look again and I go this way. Gamma here is the size of the step that you take, okay? This is a standard approach, which is very, very common. It's not the most efficient way, but in many problems where you don't have something better to do, this is what you would do. Again, the function, as I mentioned, in our case is to minimize m minus uv, which basically intuitively makes sense because that's going to make our approximation uv as close to m as possible. Here was an approximation, right? U times v is approximating m. But consider just for a minute in terms of who depends on that. It's this particular entry, right? So we can go back here. I'm sorry. This is our cost function, only considering, so over the entire j, because all of those are going to depend on x, right? This is our actual matrix entries. These are the estimated entries. We subtract them and square it up. That's our L2 norm out here. And we expand it out in terms of this. Is this clear? It's coming straight from that expression. This is my similarity. This is the objective function that we are trying to minimize. And we just expanded it out, okay? Now, what we can do is that we know that from an optimality perspective, this should be 0 at the optimal value, right? The derivative of this should be 0, right? No slope along that direction. The best guess for x is going to be derivative of this function with regards to x equal to 0. So, going in that direction, that is our expression. That's the first order optimality, dc over dx. We have a single unknown right now. We can do this. This is the expression that we just saw in the previous slide. Derivative 2 minus coming from here, vsj from this whole thing out here, right? Can you see where the derivative comes from, right? 2x derivative of the, 2y if this whole expression is y, and then dy over dx, right? So this whole thing, which will give you minus vsj. So 2 coming from the power minus vsj coming from this derivative, this whole term coming from here, right? this equal to 0, which means that I can now take this guy, rearrange items, and get the optimal value for x in terms of this expression. And we have all these values. We have the current estimates for v, u, and we have the values for m. Is this clear? So this gives you an algorithm for generating or estimating the values of u and v. How are you going to do it? Randomly pick a value of u, what we talked about as URS in this case. It's just some u from row R and column S. Compute its optimal value, set it, move on, update another value, right? You're doing some local operations out here. So one way to do this would be pick a random entry in U, update it, pick another random entry in V, update it, cycle back and forth till you're not observing sufficient changes in U and V. Or your overall cost function, which you can evaluate, which is just m minus uv, is not changing sufficiently. And at that point, you can stop. Is this clear? Right? So we have effectively derived a simple expression for doing this often. So again, choosing the elements of u and v to optimize an order, some random permutation, and then iterate, right? There is a bit of a problem here, right? We are spending a lot of time. Why is this bad? Or is there a better way to do this? So one of the problems here is that we're using a lot of data. So we are updating each entry of u and v one at a time, right? That is in itself a problem. So we need to at least visit every entry at least once, right? At least. And even that is not optimal. But during each of those visits, we are accessing a lot of data from m, u, and v together, right? So from a sort of a data perspective, m is our data, right? M is the data that we have. U and v are things that we are trying to estimate. In an ideal scenario, you do not want to constantly keep reading and writing data all the time, right? So the better way to do it is if, and this sort of goes back to what you asked some time back, is that if we brought in one reading at a time or a set of readings at a time, say all ratings corresponding to a particular item or a user or some random sampling of my matrix M, and I'm bringing that in one at a time, and I'm updating the influence of this rating on my matrices U and V together, okay? So this is sort of the data assimilation approach, which is that I'm slowly bringing in data and I'm updating my values at any given time. And this goes back to what we talked about. U and V are approximate models for our recommendation system, right? So think of it as something which is being constantly updated. As more and more data comes in, I'm updating U and V, and that's it, right? So the way you would do that is to use stochastic gradient descent. And there is a slight change, is that it can be used wherever we can take our overall objective function. This is our similarity, our misfit, BL2 norm, M minus UV, right? And if we can decompose it into the contribution of individual data points, right? And in this case, it doesn't matter if it is a single entry or a block. As long as you can decompose it, that's the level at which you can bring in data one at a time. It also helps you somewhat from a parallelization perspective. We'll talk about that a little bit later. In the case of the UV decomposition, we can decompose our cost function as a summation over ij. I'm using a double index, but you can just go over all non-blank entries of matrix M. That's the data that we have in terms of a cost function which uses Mij, right? The particular data entry, and the corresponding rows of U and V on which this guy depends, right? Because of the nature of the matrix multiplication, Mij only depends on the ith row of U and the jth column of V. And so that's the thing. So the way of looking at it here now instead is that if I have a particular rating, how should I adjust the values of the ith row of U and the jth column of V so that I'm minimizing locally, right? That's what you're doing. So this is very, very noisy if it's a single data point. If we increase it to a block, we are doing more work, which means we're spending a lot more effort in trying to get the correct gradient, because now we have a two-dimensional block of values rather than a single entry. So there are many more cross terms that you have to figure out. So the expressions for the gradient are going to look much more messier than what you have out here. It's still doable, but it makes it much more stable because you're not, now if you have the odd one user giving you a shitty rating, which is completely, like an accidental click. You wanted to rate it 5, but he clicked 1, right? Those things are going to not affect you as much. So that's the trade-off there. And you will have to deal with these kind of issues. Okay? I'm going to stop here so you can ask me questions. We have about 15 minutes at least. So understand this because I'm going to ask you guys to do this for the next assignment.
For the next assignment, are we doing blockwise or are we doing element-wise? Here you said we could do the blockwise MIJs.
Yes.
Or element-wise MIJs, right?
So the next assignment, I'm going to give you a choice. You're going to there are going to be 3 separate approaches that you can choose. So you're going to do recommendation systems. We're going to work with the Netflix dataset. You have the choice of selecting whether to do the clustering approach, which means that you would implement k-means. You can do clustering and then you can figure out recommendations based on that. You can do a stochastic gradient descent. Again, you have to make the choice. You can figure out which way you want to block it. And the third would be to do the SVD, which is what we'll cover in lecture next time. So you can do any of those approaches and see which ones you like best. So think about it. You have a choice, and I want you to think about, and again, as with some of the other assignments, you should think about why you want to use one of those approaches. And as we get closer to it, I don't think that we're going to be, the next one is probably going to be the last assignment before your project. So at least you should start thinking about your projects. Come and talk to me if you haven't. Some of you have. Those of you who haven't, start thinking about your projects. I would say that pretty soon you should email me or come and see me and get it at least somewhat approved. That's why for the next project, the next assignment, I want you guys to think about how you're going to solve it rather than just me telling you that solve this using this particular method. So think in terms of that. Yeah, I would also encourage you to sort of go beyond this and incorporate other changes. I can refer you to papers if you want, so that you can start thinking about it. It's not a full-fledged project, but I want it to be closer to a project style than what we've done so far. Okay? Any other questions? Is this clear how we figure it out and how we do this?